So now we're on to chapter 28, analysis of variance. So we are now in the situation where we have one categorical variable and one quantitative variable. So we're in the last corner of that box. We talked about two categorical variables. We used chi-square. Two quantitative variables. We used correlation and regression. And now we're in the situation where we have one of each. So this chapter is not in your book. So I posted the chapter on Moodle. So you will find that under homework data sets. You'll find the chapter, and then you'll find an extra homework assignment too to go along with a few problems from the back of chapter 28. So we use ANOVA when we have one categorical variable and one quantitative variable. So it's like the two-sample t-test where we compared two groups on a mean, only now we're not limited to two groups. We can have more than two. So for example, do high school students, college students, and graduate school students get the same amount of sleep each night on average? Well, we would need one categorical and one quantitative variable for this to work. So in this case, the categorical variable is your level of schooling. Are you in high school, college, or graduate school? And the quantitative variable would be the amount of sleep you get. So we're not talking about individual students, because surely some individual high school students are getting less and more sleep than the other levels. So we're talking about on average, as a group, how do these three compare? Why is it called analysis of variance? Well, it's called analysis of variance because that's exactly what we are doing. Our null hypothesis is the means are the same. The two-sample t-test, the two means are the same. Analysis of variance, all the means are the same. And so we want to analyze the variance, the differences. We're going to first look at the differences between the means, and then we want to say, okay, that's fine and good, but how does the difference in means compare to the random variability within each of our groups? So analysis of variance analyzes the differences between the means relative to that random variation within the groups. So let's say that Calvin students have a mean IQ of 110, and Harvard students have a mean IQ of 100, and Hope students have a mean IQ of 90. Well, we can't say anything about whether there's significant differences between Calvin, Harvard, and Hope unless we have some idea of the variation in IQ within each university. So let's say we have this situation. Now Calvin IQs range from 50 to 170, and Harvard IQs range from about 40 to 160, and so on. So huge variability in IQs for each university. Whereas over here, Calvin IQs range from 100 to 120, and Harvard from 90 to 110, and so on. So very little spread, very little spread. So what's most noticeable about the first graph? A huge range of IQs at each school. What's notable about the second graph? Well, we have very consistent IQs at each school. Very little spread, very little range within each school, very consistent. So the difference in medians over here is the big story. ANOVA analyzes means, but Boxplots show us medians. But they're both measures of center. So the big story is the difference in medians, that Calvin has a significantly higher median than Harvard or Hope. The difference in medians is important only because the IQ is so consistent from school to school. So for which of these would ANOVA decide that there's a statistically significant difference? Definitely this one, not this one. Here the difference in medians is insignificant compared to that wild variability within each group. So that's what analysis of variance is doing. It's saying, okay, how big are the differences in means? How big are the differences in means relative to that random variation within each of the groups? Okay. So what are the assumptions of analysis of variance, and how do we check them? Well, there are 4 assumptions we'll be making. And we'll be ripping paper right and left. So the 4 assumptions are first, and you won't be surprised by this one, we have simple random samples. Chose people at random to reduce bias. We also have independent groups, so there's no matching or pairing. So it's not the same people measured twice or anything like that. If we have measurements over time, repeated measures over time, then there is something called repeated measures analysis of variance. But for one-way analysis of variance, we are assuming there's no matching or pairing. We also assume that our quantitative variable has a normal distribution. So we can do a histogram for each group to make sure that's true. And then finally, we assume that we have equal standard deviations. And there's a variety of ways to check that. The one that we'll use, and they're listed in your notes, but the one that we'll be using is making sure that the biggest is not more than twice the smallest. We could check all of them to make sure they're all within a factor of 2, but if we just check the biggest and the smallest and they're close enough, then we know all the others are too. So we'll just take the biggest standard deviation over the smallest and make sure that's less than or equal to 2. If the biggest is not more than twice the smallest, then we'll say they're close enough. They're close enough. Okay, what about hypothesis testing? We'll be using the same 4-step procedure: hypotheses, test statistic, p-value, decision. I'll just keep going here. So the null hypothesis is always there's nothing going on in the population. So in this case, nothing going on is no difference in population means. So the mean of the first population is equal to the second is equal to the third, as many as we've got. And then the alternate is just that that's not so. The alternate is not that they're all different. The alternate is that it's something different from this, that maybe only 2 of them are different from each other. So the null is that all those population means are the same, and the alternate is that that's not so. Make sure that you are specifying the population mean here. We're not talking about sample means. We're talking about the means in the population. So that's step 1, hypotheses. Step 2 is an F statistic, which we'll just pluck off the output. We will never compute it. Step 3 is a p-value, which again we will just pluck off the output. Now, in here is degrees of freedom. We've always had just one source of degrees of freedom, like for the t-test, regular old one sample t-test, degrees of freedom was n-1. Now we're going to have 2, and I'll show you that in just a minute. But the first one will tell us the number of groups. It'll be the number of groups minus 1. And the second one will tell us the total sample size, because it'll be the total sample size minus the number of groups. So between our 2 different sources of degrees of freedom, we'll be able to figure out the number of groups and the total sample size. That's why we need them both. We need them both. And then, as before, we'll make a decision. So remember, if p is greater than alpha, we don't reject the null. So then we don't have any evidence that this isn't true. So we stop. We're done. As far as we know, all the means are the same. So we stop. Now, if p is less than or equal to alpha, when we reject the null, we reject that. All we know is that at least one mean is different from another. We don't know which one. So if we reject the null, we're going to follow up with what's called multiple comparisons or pairwise comparisons. And what we'll do is we'll compare this to this, 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 and this to this. So compare every mean to every other mean to see which ones differ significantly. Obviously, we're doing a lot of comparisons then, and Mr. Bonferroni would warn us about keeping our alpha at 0.05. Since we're doing lots of comparisons, that will start making type 1 errors too often. So fortunately, there are some people who have solved this problem for us, so we don't have to do all these by hand and don't have to think about lowering alpha. So there's a guy named Tukey and a guy named Chaffee who came up with these pairwise and multiple comparisons procedures. So they will compare each mean to every other mean. They will lower alpha for us. And then, of course, we only do it if we have to, if we have rejected our null hypothesis. So let's try one. We're going to compare 3 temperatures, cool, moderate, and warm, on the number of pairs of genes that factory workers can make. So let's start out with Boxplots, because side-by-side Boxplots are our choice of graph for analysis of variance. And let's see what we've got. So here's cool, here's moderate, here's warm, here's the number of blue genes that are made. So cool, median is 65, moderate, the median looks like it's about 58, and warm, the median looks like it's about 45. So, which group on average assembled the most genes? Well, on average, in this case for Boxplots, we're looking at medians. So on average, the cool group assembled the most genes, the warm group assembled the least. Are there any outliers? Remember, outliers on Boxplots are plotted separately with asterisks, and in this case we have no outliers for any of the groups. Which group was the most consistent in the number of genes assembled? Well, consistent means making the same number as each other, and so that would be this moderate group. The number of genes they made range from 50 to about 68, whereas these others are much more variable. So the group at the moderate temperatures was the most consistent in the number of genes they made. Warm had the biggest IQR. Cool and warm had similar ranges. So we can describe the means, we can look at the spreads and look for outliers. Now we'll start looking at analysis of variance output. So the first thing we get is descriptive statistics. Descriptive statistics. So this is all from StatCrunch. So the first thing is what group we've got, cool or moderate or warm. The next thing is the sample size, 8 in each group. The next is the mean number of genes that group made, that sample. So the cool group made 64.625 genes on average. The next group made 58.625 genes on average, and the warm group only made 46.25 genes on average. And then we have the standard deviation for each group and the standard error for each group. The standard error is the standard deviation divided by the square root of n, and we're just not going to worry about that. So let's look at the descriptive statistics and describe the means. Which group was the most productive on average? Well, that was the cool group, and the warm group was the least productive on average. And then we're going to check our assumption of equal standard deviations. Remember, we just want to make sure that they're all within a factor of 2, that none of them is more than twice another. So we're just going to find the biggest and the smallest. So the biggest is 12.08. The smallest is 6.413. We divide that out and we get 1.88. That is less than or equal to 2. So yes, the standard deviations are equal. Obviously they're not exactly equal, but they're close enough. Close enough for us to consider them equal. So we've looked at our descriptive statistics, groups, sample size, means, and standard deviations. Now we'll move on to the analysis of variance table. So now it's time to do some hypothesis testing. We've seen what we saw in our sample. Now we want to try to draw conclusions about the entire population. Everybody who's working in cool versus moderate versus warm conditions, how are they doing in the making genes department? So first, what are our hypotheses? Well, the null hypothesis is that the mean number of genes that people are making in cool conditions is equal to the same as moderate and warm. And then the alternate is that that's not so. So in words, the mean number of genes made under these three conditions is the same. There's absolutely no difference in the average number of genes made under these conditions. Remember, we're talking about the mean. So surely some people who are working in cool conditions are taking longer than some people who are producing fewer genes than those who are working in warm conditions. But on average, what's true? The group as a whole. What's true for the group as a whole? So those are our hypotheses. Now we want the F statistic, degrees of freedom, and p-value. So here's our F statistic. Here's our degrees of freedom. We need both of them. The 2 is the number of groups minus 1. So we have cool, moderate, warm. 3 groups minus 1 gives us 2. And the degrees of freedom that goes with the error is the total sample size minus the number of groups. In this case, our total sample size was 24 workers. 24 workers minus 3 groups gives us 21. So we need both of those, the 2 and the 21, and there's the p-value, 0.0065. So what do you conclude? Well, that p-value is less than or equal to alpha, so we reject the null hypothesis. So we reject that all the means are the same. These groups are not making the same number of genes on average. Now we need to find out which one or which ones are different from each other. So we need these pairwise comparisons. So now let's look at the last part of the output. And see what we get here from StatCrunch. So here's what we get. These are two key pairwise comparisons, and how it looks, it does this by first comparing cool to moderate. The difference is the difference in sample means. So if you look back at the sample means, we can get this up. Oh, one more. The difference in sample means between cool and moderate is 64.625 minus 58.625. So the difference, 64 minus 58, is 6. You don't have to worry about the negative, that's just the way they're subtracting. They were subtracting moderate minus cool and got a minus 6. But the difference is 6 genes on average, 6 pairs of genes on average. So that is a difference in sample means. Then we have lower and upper. That is a 95% confidence interval for the difference in population means. So first we have the difference in sample means, then we have a confidence interval for the difference in population means. So if we looked at all people working in cool conditions versus all people who are working in moderate temperature conditions, what's the sort of difference in the number of genes they make? What would we expect to see? In this case, it's minus 19 to a positive 7. So if you think about back to chapter 24, where we talked about a confidence interval for a difference, the key number in a confidence interval for a difference is 0. Because if 0 is in that confidence interval, then we think there is no difference. So in this case, we think there is no significant difference between those working in cool temperatures and those working in moderate conditions in the average number of genes that they make. And the p-value backs that up. There's the p-value for testing if there's a significant difference between cool and moderate temperatures in the average number of genes. That is greater than 0.05, so there is no significant difference between the number of genes made when working in cool or moderate conditions. So let's keep going here. We do need pairwise comparisons. Here they are. So the difference is the difference in sample means. Lower to upper is the 95% confidence interval for the difference in population means, and the p-value is testing if those means are the same. So really this is superfluous because we already knew from a confidence interval going from a negative to a positive that there was no significant difference. Okay, which means differ significantly from each other? Well, let's look at the p-values. This one is greater than 0.05. This one is less than or equal to 0.05. This one is greater than 0.05. So the one that for which there's a significant difference is cool and warm. Cool and warm are significantly different. And the other way we know is that if we look at this confidence interval for the difference, we have negative 31.51 to negative 5.24. So cool and warm conditions result in significantly different number of genes. And we knew that because the p-value is equal to 0.0055, that is less than or equal to 0.05, so we reject equal means. Remember, the null is always that there's nothing going on. So we're rejecting that there's nothing going on and believing that there's a difference. So reject the null of no difference. And the other way we knew was that the confidence interval doesn't contain 0. So we think the difference is unlikely to be 0. We think there's a real difference. Again, no significant difference from moderate to warm because that p-value was greater than 0.05. If we were to compute the mean number of genes assembled by all people working in cool conditions and all people working in warm conditions, So we're talking about the population means. What do we think the size of the difference in means is? We're comparing cool to warm. We think the difference is somewhere between 5 and 31.5 genes. So we know from before that they were making more genes in cool conditions. So we are 95% confident that all people working in cool conditions, on average, are making somewhere between 5 and 31.5 more pairs of genes than people working in, than all people, the population of people working in warm conditions. So analysis of variance, we've got one categorical, one quantitative variable. The whole idea is, how does the difference in means compare to the random variation within a group? What's the important story? If the difference in means is the important story, then analysis of variance will tell us that. Our null hypothesis, there is no difference. We test it with an F statistic, a p-value. If we conclude that there's a difference somewhere, then we follow up with these pairwise comparisons to decide where the differences lie.